Hi everybody, my name is Sarah Oppold. I'm from the University of Stuttgart and I'm happy to present our exploratory paper, a system framework for personalized and transparent data-driven decisions, as part of the CAiSE 2020 conference. I'll start my talk with a motivating example, illustrating what we understand by data-driven decisions and why they can be problematic. Imagine there's a company Best Job which wants to offer an online job market. For this purpose, their developers should develop a decision support system. The system should recommend the most suitable job offers for each job-seeking user based on their user profile. Therefore, the developers make use of historical data associating people with appropriate jobs and use this data to train machine learning models. Based on these models, they recommend the most suitable job offers to users, thereby supporting the users in making the decision for which job to apply. This is one example for data-driven decision support systems, which are used in a variety of applications today. However, these systems may be flawed. Problems can arise due to dirty or biased data. For example, Best Job's historical data could disadvantage female people by associating them with less paying jobs. This flawed data or wrong decisions in the development process can lead to imperfect or biased machine learning models, which in turn will lead to imperfect, in this example maybe even discriminating decisions. This is not a fictional problem, as these news headline examples show. In fact, Google is less likely to show ads for high-paying jobs to women. Amazon failed to create a hiring tool that does not discriminate women. Even government use computer programs such as the recidivism prediction system COMPAS that inadvertently is biased against people of color. While researchers from different areas are working on creating better data and machine learning models, we argue that the decisions made by decision support systems will never be perfect. Therefore, we devise a new vision of responsible systems that allow us to provably get as responsible as we can practically get. In other words, we can never have perfect systems, but we want to develop systems that work as good as possible while proving that we have done everything in our power to achieve this. As a first step towards this vision, we present today a system framework for personalized and transparent data-driven decisions. Before I describe the system framework, let me explain more clearly what we mean by the non-functional requirements stated in our vision and the paper title. What does as good as possible, personalization, and transparency mean in this context? First, the decision support systems should have high quality. They should use the optimal model with respect to multiple quality metrics and meeting additional quality criteria. For example, the set of models M1 to M4 on the right was not only assessed with respect to accuracy, but also some fairness metrics, and the system should now use the optimal model. While it is clear that M1 has highest accuracy and M4 has the highest fairness value, it is not always easy to determine which is the optimal model when considering multiple dimensions. One possibility to solve this conflict is that the system should value higher fairness over higher accuracy, so M4 is determined as the optimal model for this example. Second, the decision support system should make personalized decisions. That is, in addition to adapting the choice of the used model to quality requirements in general, the quality has to be assessed depending on the user or user group profile in order to make the best decisions possible. For example, we could consider dividing the users based on their gender. Again, we assess the models with respect to accuracy and fairness, but in these user groups, which leads to the diagram shown on the right. While M4 could be chosen for male users as described earlier, M1 clearly outperforms M4 for female users. Therefore, the system would use the model M1 to assess female users and M4 for male users. Finally, the system should be transparent. This basically means that it should account for the definition and use of a model in order to prove that everything in our power has been done to create the best system possible. For example, a disclaimer such as the one shown on the right could be shown to users. It informs them that an automated algorithm is used and what variables it depends on, what the results have been optimized for, what risks are associated with using the determined model, and everything in simple words. In order to develop decision support systems that fulfill all of these non-functional requirements, we present our system framework. Therefore, we extend the simple framework which consists of a data component and a model component, and which Best Job has used in the motivating example. A new quality component is added, which contains quality specifications that store the quality criteria and optimization goals for the system. As you can see, in addition to users and developers, a third category of stakeholders, which we call regulators, are involved in devising such quality specifications. We will not go into detail about them or how they interact with the system during this talk, but you can find more details in our paper. Based on these quality specifications and the trained models in the model component, model ensembles are generated in a model ensemble component. We use an algorithm which we call optimizer to determine the best personalized models for each individual user or user group, and thus form the mentioned model ensembles. Finally, we make use of metadata in order to provide transparency. Therefore, each object in this system, such as dataset, model, or model ensemble, is described in metadata sheets, or abbreviated MDS. These metadata sheets are mapped to a unified format and then stored in the metadata component. From there, the metadata can be queried by the different stakeholders to prove the quality of the system. Additionally, the metadata is queried by the optimizer in order to improve the model ensemble creation. This completes the system framework for personalized and transparent decisions. Next, I'll discuss three of the new parts of the system in more detail, namely quality specifications, the optimizer, and metadata sheets. The quality specifications are encapsulated in the quality component and specify the optimization goals of the system. They should define for a given state or context the desired state to be achieved by the system. While modeling them is a challenge in itself, it leads to new interesting challenges. For one, different views of the stakeholders can lead to conflicting specifications. Given these conflicts and multiple quality dimensions, can we determine a minimal set of quality specification that is representative of the full collection? To illustrate how such quality specifications could be modeled, we defined them as three tuples with a set of optimization goals, or G, a set of constraints, C, that the model should additionally satisfy, and a definition for a given state, S, which for example could be a user profile or a user group profile. A quality specification aiming at maximizing accuracy of the system for female users could then be described by such JSON documents. The optimization goal is specified by metric and direction, here accuracy and max, and for the female user group, in this case expressed by a dataset specific value for a specific variable. These quality specifications are one input to the optimizer, which aims at selecting the best models for each individual user or group of users, which is specified in the quality specification. Where there is existing research in this area, the framework introduces new interesting challenges which have not yet been solved. For example, what are new model ensemble algorithms which create a minimal set of model ensembles for these optimization goals? Or how can we determine a set of models that are optimally suited as input to the model ensemble component? This pseudocode shows how dynamic model selection could work. Input to the algorithm is a quality specification as defined above and a set of models M1 to Mn. The algorithm will return a list of models ranked by their quality with respect to the quality specification, which here stands for a model ensemble. First, all models which do not violate the quality constraint C specified in the quality specification are added to a set of valid models. These are then input to a method called dynamic classifier selection by local accuracy, which ranks a set of models dependent on the model accuracy for similar data points. Next, metadata has to be created in form of metadata sheets and added to the MDS store before finally the list of sorted models can be returned. While existing algorithms such as the DCSLA can solve the local quality problem for accuracy, the framework has to be able to optimize for other metrics and multiple metrics at the same time to determine the model ensemble. Therefore, we need new algorithms. Finally, metadata sheets are one or more metadata documents describing datasets, models, or model ensembles which are part of the decision support system. Since these metadata sheets could be very large, ideally they are populated automatically. Since the metadata is queried by the optimizer for selecting models, as well as by different stakeholders, various metadata has to be captured for transparency and personalization. Although research already exists in this area, the framework raises new challenges. For one, given the diverse query workload, what metadata has to be modeled in order to provide both transparency and personalization? Also, what methods and algorithms can be used to populate the metadata sheets automatically? As an example, let us have a closer look at metadata sheets for datasets. Queries relevant in terms of personalization may be: what is the structure of the dataset, or what is its quality? The various stakeholders may ask additional questions in order to assess the quality of the system. For example, who created the dataset? What was the intended purpose? Or how was it processed? Or how have the data subjects given consent to the processing of their personal data? All information necessary to answer these questions could be stored in a semi-structured format, such as this small snippet of a JSON metadata sheet. In order to perform a use case-based validation of our system framework, we have developed the first prototypical implementation called Loopy, which stands for Lucid Personalization. It is based on existing methods only. We have performed the quantitative evaluation of personalization, as well as a use case demonstrating transparency, which I will describe now briefly. With Loopy, we have developed a decision support system where a model is selected based on gender. What does this mean? We have trained a set of 10 different models, as can be seen on the table on the right side. Usually, the model with the best accuracy for all test objects is used for all users, which in this case is M6. For gender-based personalization, we have also assessed the accuracy of the models for female and male test objects separately. As you can see, while M6 performs best for male test objects, M1 performs best for female test objects. Thus, the system uses different models depending on the gender of the user. With personalization, the overall accuracy of the system increases slightly. Using the metadata sheets, we could identify class imbalance in the training data as one likely reason for why Loopy did not perform better. Further research is needed in order to improve the set of trained models as input to the model ensembles. Loopy also offers transparency to different stakeholders. To users, an informed consent interface is presented, including a general disclaimer on top, explaining the application, and personalized performance information below, displaying the set of available models along with their test performance. A second interface illustrates the components and their connections, as well as basic information stored in the respective metadata sheets to regulators and developers. Using these interfaces, Loopy is able to give an overview on possibly complex systems, but a lot of additional metadata is necessary to support a wide range of possible queries. Also, systematic studies need to be conducted in order to assess and improve these interfaces. In conclusion, we present a system framework for personalized and transparent data-driven decisions as a first step towards our vision. This framework is still in its exploratory stage, and it may take years to investigate all open research questions. However, with the prototypical implementation Loopy, we could demonstrate the framework's pertinence to filling the gap in providing personalized and transparent decision support systems. While further research is needed to solve the challenges already mentioned, additional research is needed also in other directions. These include security and privacy of the system, the reduction of ramp-up costs, and resolving the tension between transparency and intellectual property. Thank you very much for your attention. You will find further details about the framework in our paper. Bye, everybody.